This part is going to be about MRI. I think I'll give you also the image formation for MRI. It's a little bit different concept, but I will try to simplify it. And then next time, not the next lecture, I think the last one, the one that talks about clinical application, I will use it, or applications of imaging for malignancies. I will extend it to actually include more clinical application for CT and MRI. And I think this is what's mostly important for you at this level. But I thought we will get rid of the background of imaging foundation today. Okay. Do you see my screen? Yes, no? Okay, thank you. All right, so so this part is going to be about introduction to magnetic resonance imaging. So this is another imaging modality. The last you will, well, the one before the last you will learn about in this course. So you have learned about X-rays, you have learned about CTs today, which is similar concept. You have learned about ultrasound. Today you will learn about MRI as well. And then next time we'll talk about nuclear medicine and PET. So we will cover basic concepts, how signal is being generated. We will talk about what is known as a basic pulse sequence. And then we'll talk about tissue contrast, which is again similar to CT, but even in a better way, an advantage of using this imaging modality. One of the main advantages of using MRI is the fact that it uses non-ionizing radiation. Remember in the first lecture, we talked about the spectra of the different electromagnetic radiation, and we said that MRI, or we said that there is a range in medical imaging which is within the non-ionizing range, and ultrasound is 1, MRI is 2. So these are the 2 imaging modalities where you actually can image without ionizing radiation being used. It relies on signal generated based on a phenomenon known as nuclear magnetic resonance. We'll talk about that. But the imaging modality itself is the modality that allows the conversion of these signal into an image. So you have a signal that is being generated using a phenomena or by a phenomenon known as nuclear magnetic resonance, but then the imaging part relies on using the conversion of the signal to an image. There are 3 concepts behind that. The nuclear concept, which means that our body is composed of atoms. Atoms that have odd number of protons, like for example, the hydrogen will exhibit a specific feature, which is a net momentum. And then this momentum will make the atoms spin. And since we have too many hydrogen atoms in our body, in water, in fat, in protein or muscles, we could say that our body is composed of spins. So hydrogen is the most useful spin in MRI, but it's also the most useful spin in our body. It's actually the highest contribution of our body in terms of atoms. The second part is what is meant by, or is the magnetic part. When charged particles rotate or spin, they can actually generate magnetic fields. But the other way is true. Alternating magnetic fields or magnetic fields can also induce charge. And this relationship between the magnetic field and between the charged particle, which are in this case the hydrogen atoms, are the foundation of the signal generation and image formation by MRI. Now remember that in the rest status, these atoms in the body have no specific direction. So they are actually spinning around in very random motion, and therefore their energy are cancelled out because these energies, each one of them is in one direction. When we align these spins in one direction, we actually can get a net magnetic field of a relatively low energy state. And usually we do that forcibly by putting the patient inside the MRI machine. Well, we don't force the patient, but we force the spins in the body to actually align in one direction with some of them in the opposite. And that gives us a net energy, which is relatively low status or low state energy. And this is when we take the patient and we put him inside the MRI machine. So when the patient is put inside, once the patient is put in an MRI scanner, the spins will align. And even though this is important, it's not good enough because we need to interact with the spins in the body, so different atoms, including the hydrogen, to generate a signal. And to do that, we need to have different components within an MRI scanner. We talked about the main magnetic field, which is this part here. But then inside the main magnetic field, or the main magnet, there are actually different coils, and each one of them is acting as a source of waves. We will talk about that in a bit. And these are arranged in the 3 different directions. So one is known as the X, and one is known as the Y, and then the Z, which is actually along the longitudinal axis of the patient. These are transmitting coils. So these are coils that transmit energy. And then we have one that receives the signal. But remember that nowadays we have also the coils that actually transmit and receive. Okay, sorry. The last part, or the last concept of importance in generating the signal is the resonance. And this is basically when you interact by sending waves to the body, which contains the spins, i.e. the hydrogen atoms mostly. For an interaction to take place, they must be at the same radio frequency. Okay? So remember, simple concepts. If I want to listen to the music, my ear need to have ability or need to be able to match those frequencies in the, let's say, the radio. I am not able to hear every possible sound because their frequencies might not be frequencies that I'm able to detect. So in a similar concept, for resonance to take place, I need to interact with the protons, whom I could predict their frequency by using radio frequency or waves of a certain radio frequency that matches their radio frequency. And when that happens, we get something called or we can interact with them. Also, if I want to receive from these spins, I need to have a matching radio frequency. So it's just like a channel that I turn on at different frequencies to be able to detect or send waves. Let's say, for example, I have protons in the body. The closer ones, their radio frequency 70. The one that is further is 60. By knowing that the distance changes the frequency, I could actually have the ability to interact with spins that are further from the receiver coil and the transmitting coil by using a different frequency. So once I set it on 60, I know that the interaction will happen with B spins rather than A spins. The same thing, when B spins resonate back and precess, I will get only signal from them. I will not get signal from the spins annotated A, because their frequency is different. Now, obviously, we don't have this sharp demarcation of 60 and 70. We have usually a bandwidth or a range of radio frequencies, with a center being probably around 60 and then a little bit away from it, and the signal weakens as we move away from the 60. Now, very important also in MRI to understand a concept known as MRI susceptibility. MRI susceptibility basically means, sorry, I don't know what happened. Yeah, simply means you have a structures that act like magnets, and their characteristics are dependent on the material or the atoms that they are in. Now, most of the material that we have in our body are known as diamagnetic. So, and this means that the characteristics of them allows them to have magnetic susceptibility that is less than the main magnetic field. Now, paramagnetic are slightly larger than the main magnetic field, and therefore they are often used as contrast material in MRI. Ferromagnetic means much larger, and these are the ones that actually interfere with the image, either hardware, metal, etc. So most of our tissues are very close to the main magnetic field, slightly less. Paramagnetic, slightly larger than the magnetic field, and they are often used as contrast material. And ferromagnetic, much larger, and therefore they cause disruption of the image. Sometimes we use that disruption actually to get more information. Now, we talked about the spins in the body, the phenomena of nuclear magnetic resonance, and we said it's called nuclear because there are protons in the nucleus, which are the main source of the magnetic spin. And then we talked about the magnetic field being generated, but also the ability to react or interact with the spins via magnetic fields. And that's why one way to think about the MRI scanner itself is that it is a large magnet which allows the spins to align, and therefore only a small signal will appear, but then multiple coils which are mainly there to transmit, but they could also be used for receiving. And then obviously the resonance part, which is simply a matter of matching radio frequencies. But to get the image, we need to actually go through a step-by-step approach which I will try to simplify because this was a lecture that was developed before, and I realized over time that it's probably better to simplify it. We talked about this part, and we said the first thing is that we place the patient inside the magnet, and this will be causing alignment of the spins in one direction with only few that are opposite to them and the small energy level. This is called the B0. But then if you don't interact anymore, you will not get any image because all of the protons now will look alike. So the next step is to excite them by applying different pulses. That's why we have the transmitting coils, the X, Y, and Z. And then you will collect the resonance back, the signal back. All of this is known as nuclear magnetic resonance until you apply what is known as the Fourier fast transformation, and you actually reconstruct the image. We will not touch on this at all. Now, why do we need to use a basic, why do we need to apply a B0? Why do we need to have that basic alignment? Well, if I ask you a question, who is faster on this image? And because we're online, it might not be easy. One of you might say, well, this is the faster because this is the one on the front of the group. But you could also say, well, it's possible that this image is angled and this is the person who is faster because he's also on the outer ring, which is likely to be the, which means that it's also the longest distance. Or you could say, well, we wouldn't know because this might be in his first or second lap, while this might be in his third or fourth lap. So even this one could even be faster. So a single snapshot of different people can be used as a concept to understand how, if I am going to get different frequencies from different resonance waves from the different protons in the body without having a baseline, so without knowing where they were starting from, can be misleading, and therefore actual image interpretation or image formation is not possible. And the best way to do that is actually to make sure that they are all aligned together. And then I know they have started at the same line, I know the distance, and then I could actually record the motion and see who will be the faster one. So B0 will allow this differential signal from spins to be detected at baseline. But then we apply a pulse to excite them. And by exciting them, we give them the ability to be near to full magnetization. And then when they relax, when they go back to their relaxation status, this is when I start collecting the signal. So we collect actually during the relaxation, meaning the spin is actually now going back to its relaxed state. We can use encoding to actually determine which part of the body to image. For example, we can select a slice of tissue. I could select to image the brain versus the pelvis, but I could also within the brain select to focus on the orbits rather than the base of the skull. And selecting a slice of tissue will simply be dependent on the frequency that is expected for each location, depending on the known tissue. Now, not only you can select the slice, but you can also receive simultaneously at the same time resonance by the same coil. So you can actually send so transmit and receive at the same time. Now we keep on repeating those steps of excitation and relaxation, excitation and relaxation, until we collect enough information about the different spins in the body. I'm not going to go through the timeline because I think it's just a bit complex. But what I would like to maybe focus more on is the relaxation times. Now, remember that the spins are going to rotate, and then they will start to relax. And as they relax, this is the time when during the relaxation is I am collecting information. Now, there are two types of relaxation. One of them is known as the T1 relaxation time, and one of them is the T2 relaxation time. And they are related to the fact that when the spin is rotating, it's actually rotating in not a 2D, but in a 3D space. So there is a plane that the relaxation is more longitudinal, which is the T1, and there is one which is more horizontal. That's why you see it going to the x-axis, and this is actually the T2 relaxation. So the spins are actually, yes, rotating, but they are rotating in space within a three-dimensional space. The relaxation times have been studied. So now we know, for example, water has a T1 relaxation. So from the fully excited status until it reaches, until it picks up 2/3 or 67% of its signal, we know that it takes about 4,000 milliseconds, sorry, or 4 seconds. T2 relaxation for water is shorter. And it's 2,000 seconds. Fat has a relatively long T1 relaxation, short T2 relaxation. Now, knowing these numbers is not important, but what is important is to know that because material has different relaxation times, I can interact with them in different ways to actually get better differentiation of them. For example, I can use MRI with different types of sequences to be able to differentiate between fat, muscle, and fluid. And they have more characteristic depending, or different characteristics depending on the type of sequence that I used. I said I don't want to go through the sequence or how the sequences are being built because I thought it's more important. But at the end, there are different types of sequences. One of them is called the T1 sequence. And basically, this is a sequence that has short relaxation and short excitation times. And because the excitation and the relaxation times are short, when you have a material that has a long T1 relaxation, it would actually have lost its signal, so became dark or black by the time you acquire the image. Fat, on the other hand, because it has a relatively short T1 relaxation time, it would pick up signal before you would have completed your sequence, and therefore the signal is actually quite high. T2, on the other hand, the T2 relaxation at 2,000, which is enough for the signal to be picked up on MRI. Fat will be picked up, but not as intense as it is on T1. So what does that mean when it comes to image? So this is a cross-sectional image of the pelvis. This is a T1 weighted sequence. Now, T1 weighted sequence can be used without contrast, but also with contrast. And we know this is an image with contrast because the vessels here which are the femoral artery and veins, are actually high signal. And they are high signal because there is gadolinium that was injected. So this is a T1 weighted image. This is also a T1 weighted image, but this is without contrast and this is with contrast. This is the urinary bladder. Remember, we mentioned that the water is going to appear low signal intensity or black on T1. So urine will be the same. Fat is bright on T1, and that's why all the subcutaneous fat is actually bright. And then the muscles are intermediate. Now, this is a T1 weighted signal, and you might ask, well, why I don't see fat? Simply because we used a radio frequency to suppress the signal from fat. And this is because fat is bright. And if I give gadolinium and I opacify the vessels, I might not be able to differentiate between the vessels and between the fat. So I actually suppress the signal of fat, and this will allow me to see only the structure that are enhanced with gadolinium. So this is a better way to improve image quality, and it is also using one of the advantages of MRI in terms of being very selective and specifically focused on different tissues. T2 weighted sequence, long TR, long excitation, so it takes longer time to actually build the magnetization, and then to listen to the echo, you even take a longer time. Now, because water is actually of relatively long signal, long T1 and T2, and because I take already longer time, so I will have time to pick up the signal from the water, which will appear bright or high signal. So, for example, opposite to T1, where the urine had a dark signal, here urine, which has fluid or water in it, appears very bright or high signal intensity. Fat is sort of intermediate compared to T1. This is another differentiation between T1 and T2 weighted images. So T1, T2 weighted images. For example, here you can see, this is an image of the brain, and they are both at the same level, at the level of the lateral ventricles. Now, this one, T2 weighted image, you can see that the lateral ventricles, which contain CSF, and so are the spaces around the brain surface, they're actually very bright. So this is CSF, a high signal, T2 weighted sequence. In comparison, we see the highest signal here is in the white matter, which is in the middle of the brain. And this is because white matter actually contains fat. And remember, we said fat appears very bright on T1 weighted sequence, while the CSF in the lateral ventricle is actually very dark or very low signal intensity. So this is another way also to look or to see how we can differentiate between different tissues using T1 and T2 weighted sequences. Gradient echoes, the main advantage of them is that they do not wait for a complete 90-degree pulse, but they excite at smaller degrees, and that's why they are usually faster. But they also have a problem of being very susceptible to magnetic inhomogeneity. So, for example, if I have a metallic hardware, which is MRI compatible, but it's still metallic, or if I have, blood degradation products, they will appear very dark on gradient echo sequence. But at the same time, because they're acquired at a very fast time, very quickly, the image quality is of high value in the in the imaging, for example, of the heart, because cardiac imaging is done while the heart is moving. And therefore, if I am able to acquire images very fast, like by using gradient echo, sorry for that. Okay. Yeah. So this finishes this part. Now, I do realize there is still more time, but I am not sure you want to continue with the clinical applications for MRI. We can do it in 20 minutes, or we could leave it with the other lecture on malignancies. I prefer to do that because I want you to see the difference between MRI images and CT. Plus, it will be too fast to go through 20 more slides. So, I'm asking you. Yes, no? You want to continue? If you continue, we'll go through, yeah, okay, I agree. I think it's and it's not going to be the same for the other lectures. This is because there is a lot of physics and background of images. I realize it's a bit heavy. That's why I think it's better to leave the clinical part later on, or the clinical applications. So I will stop here. Do you have any questions? Okay, what I will do, I will modify the slides a little bit. I want to avoid sending you something that we didn't detail and you might not need for the purpose of the exam. So I'll just remove those parts and then I'll share them, if not by today, by tomorrow, but remind me. If I forget, please just send me a text on WhatsApp or an email to send you the lecture. Okay? Thank you.